Good morning, everybody. My name is James Young. I work for a company called True Blue Power. We're a division of Mid-Continent Instruments and Avionics. And what we're here to talk about today are lithium-ion batteries, specifically main ship batteries. And again, I'm the tech support engineer for the division known as True Blue Power. So kind of a brief outline of what we're going to talk about today. We're going to do a company overview, a brief history of who we are, what we do, what we provide to the aviation community, why we decided to start to push the technology of lithium-ion in aviation. We're going to go into some of the subsects of what that is and what that entails to get that on your aircraft, the safety and the design, the safety by testing, the operational characteristics, general maintenance. That's going to be more what we're going to be interested and focused on here for today's discussion, and some of the typical installations that we have on some Type Cert aircraft and some STC aircraft that are currently flying today. So again, I work for True Blue Power, which you'll see over here on the right. We're an offshoot, a branch of Mid-Continent Instruments and Avionics. The business is in Wichita, Kansas for its headquarters. It's been in general aviation and commercial aviation for avionics and instrumentation for over 52 years. The headquarters is in Wichita, Kansas, but we also have a second office in Van Nuys, California, outside of LA. But we have a wider footprint through that in our authorized distributors and our repair and overhaul facilities. We have 12 worldwide distributors and 3,000 active dealers. So any continent, especially the United States, Europe, and anywhere, we have our product and our name and our distributors out there to sell you and parts and to get your parts overhauled. This is our facility in Wichita, Kansas. It's out by Colonel James Jabara Airport on the northeast side of town, and this location has been there since 1999. And then our sales and repair facility is also in Van Nuys, California. Again, that's outside of LA. On the instrumentation side of the house, you're going to get your basic, your gyros, your avionics and radios and things like that, repair and overhaul, gauges, some software development, and some good examples of what that side produces would be things like your 2-inch CDI indicators, like this MD222. And then we also produce this MD302. It's a standby attitude module, also known as SAM for short. It's all solid state, lithium-ion battery backup in case a ship's power is lost, things like that. You can see that it's mounted vertically like this, or you can also mount it horizontally. We'll see these in a lot of aftermarket STCs, and some aircraft actually roll off the production line with these installed as a standby. And then where I work at True Blue Power, pretty much everything that's going to provide emergency power, standard power for your aircraft, with the exception of things like alternators and generators. We pretty much produce everything else. So DC to DC converters, AC inverters, AC to DC converters, USB charging ports that can be either sidewall mounted or instrument panel mounted, seat mounted, however you'd like. They're pretty flexible. They're very popular. Various other power supplies, custom battery packs if needed, and then what we're here to talk about today would be something like this. This is the TB44 lithium-ion aircraft battery. It's kind of comparable to, in size, dimensionally, of what like a Concorde RG44 would be. So why did we decide to go with this in technology and aviation? Pretty simple. Is when you look at the battery technology comparisons, everybody's familiar with lead acid and NiCad. And those are great batteries for certain things, but the lead acid technology has been around more or less since the 1800s, mid-1800s. They're very cold temperature, performance tolerant, and abuse tolerant. They have a limited life though. On average, a lot of people can replace those as often as once a year to every couple of years. And then if you've ever changed a 40 to 50 amp hour lead acid battery out of a tail cone out of like a Cessna 500 or something like that, like I have, you know, it's not easy because that's about a battery weighs about as much as I do. I'm not a big guy, so it's not fun changing those. NiCad was an improvement on that. You still had, you know, good temperature performance, but you got a little bit more power for engine start, and you got a little bit more longevity for emergency power situations. However, pound for pound, they're about as heavy as a lead acid battery, and their metal in both of those batteries, whether it's nickel cadmium or lead acid, it's a toxic material. So once the battery's reached the end of its life cycle, getting that battery disposed of can be kind of a hassle. So we decided to look into something different. So we went with lithium-ion. And if any of you guys have ever used a DeWalt drill and it went from the nickel cadmium batteries to your lithium-ion batteries, you notice that it was a lot better performance and it was a lot easier to move that drill around. Same principle applies here to the lithium-ion batteries. We get on average about 40 to 45% weight savings as compared to a typical lead acid or nickel cadmium battery. What that results in us being able to have that battery at that small of a weight as compared to the other chemistries, we are 3 times as energy dense per kilogram by weight of material than a lead acid or a nickel cadmium battery. We also don't have a memory effect problem like NiCads have. After a NiCad has had some time on it, its 0 point creeps up on you, and you lose capacity based off of that. Battery that used to last you, you know, a couple hours on your emergency load, if it was small, might only last you an hour, might only last 20 minutes, and you have to send the battery to an overhaul shop and get it, you know, either cells replaced or deep cycled, et cetera, et cetera. We don't have that problem. And then the one drawback, it's not all completely positive. Everything has cons. We have a requirement that we have to put in what is known as a battery management system to control the charging and discharging rates and things like that. Not really a problem. It's just an extra consideration that we at True Blue Power have taken into consideration in the design of our battery products. At True Blue Power, we define the 2 terms, power and energy, a little uniquely. Power is the ability to move with force. This is going to be starting your main aircraft engines, your APUs, kicking on high amperage loads for short periods of time. Energy, the ability to move loads at a long distance. That's when your main ship batteries are now into an emergency power mode. You've lost generation, and now you need to carry critical loads such as nav equipment, maybe life support equipment if you're a medevac aircraft, things like that for long periods of time. So this chart here gives us a better chemistry comparison of another reason, just a real good graphic of why we chose lithium-ion. So in the orange here, you'll see lead acid. On the bottom, you'll see energy. This is how long we can carry a load for a given amount of time. On the vertical axis, this is our starting amps, our cold cranking amps, if you will. And you can see lead acid is kind of here at the back of the pack. And then as we've discussed, nickel cadmium batteries, or NiCad for short, they got a little better. You got a little bit more longevity, and then you have some more cranking amps. Smaller or lesser known nickel metal hydride was an improvement upon that, but it's not really seen all that much in aviation. And then we have lithium-ion. We're all aware of what that is now, and you get substantially longer emergency load times and then substantially higher cranking amps for high power applications for those short bursts. In these dashed lines here, that's where the True Blue Power product lines fall within. So we're kind of at the upper echelon and the midpoints for all of those. And as you can see, we're very much so significantly improved over the NiCad and the lead acid chemistries. Battery safety and design for the lithium-ion. A lot of people don't realize this. within the lithium-ion family, there's not just one chemistry called lithium-ion. There's actually subset chemistries. So what you'll see is that you have what is known as metal oxides. And these will have things like manganese, lithium, nickel, manganese, cobalt, nickel, cobalt, aluminum, and then what we use, lithium iron phosphate. And this chart shows why we chose that chemistry, that subset chemistry underneath the whole lithium-ion umbrella. What you see across these 5 metrics, energy, power, safety, life, and cost, all of them can do very good things. We don't have anything on this chart that is necessarily a negative, but if you notice, the lithium iron phosphate has top marks for safety without really sacrificing power, energy, life, or cost. But that being in aviation, that is our first and foremost concern with any product that any of us make in this industry, is the safety. So we chose the lithium iron phosphate without having to sacrifice on any of the other metrics. So you still get the performance, but you have the peace of mind of having a safe product in your aircraft. Our design philosophy is to monitor, mitigate, and contain. So we kind of use sports analogies to kind of relate that, how our circuitry inside our battery works. So much in the way that this hockey coach is monitoring his game and taking in real key time information, that's what our battery management system does, our BMS. It monitors things such as internal temperatures, the currents coming in and out of the battery, voltages as they relate to the battery. And based on that, he's going to make decisions to take things and adjust as necessary, much as the way that a coach might change their strategy of the plays that they're making. So in this example, our batteries can have anywhere from 16 cells to 152 cells. So we might take into consideration that we need to balance those cells out, which would be equalizing the voltage to get them all within the same tolerance. So our circuitry is capable of that, and that's the example. We can balance cells within a module or a cell pack. Mitigate is another one. If all the other control measures, such as cell balancing or something of that nature, aren't going, we can literally electronically remove individual cells and modules of cells from the battery until they come back within tolerance, and then bring them online. Use the maintainer, pilot, owner, operator will never even know that that has happened unless it's become fault condition, which just doesn't really happen. And we'll just have that battery portion, those cells or those packs, taken out of the equation. Your overall battery voltage didn't change because of the parallel configurations internal to the battery. And then once it comes back within tolerance, it gets back online. So analogous to this referee calling a timeout. And then last but not least, we have mechanical fail-safes. If the battery management system for all the monitoring, mitigation has failed, your battery is either going to be built out of anodized aluminum or a powder-coated steel case with a vent tube that vents any electrolyte vapor outside the pressure vessel, outside of the aircraft. And so that would be these guys going to the penalty box, essentially. Some of our design features that we philosophize and that we make sure each one of our batteries has: overcharge protection, over discharge, over current, short circuit, over temperature, under temperature, which is also a key battery performance no matter what chemistry you have. If you're operating in cold environments, it's whether you're a lead acid or a nickel cadmium battery or a lithium ion, having the battery warmed up to optimum temperature is better for your engine starts. You get better power delivery, so we do that. We provide battery status and health communications up to the instrumentation panels up in the cockpit for view. And then if you're on a smaller aircraft, such as a, say like some smaller rotor aircraft, or maybe a small single engine piston driven aircraft that has a small DC generation system, after an engine start, our smaller battery, the TB17, will self-limit the charging current so we don't overload your gen system. Built-in mechanical protection. We have thermal insulation and separators. So if all of the cells in that battery were to go into a thermal runaway situation, it's not going to damage your aircraft structure, your wire harnesses, your insulation blankets, or anything of that nature. We have some high current fuses, thermal fusible links, which is actually a fuse link that will fall away from a bus bar if it gets hot enough to basically disconnect the battery from the electrical loads on the aircraft. And then last but not least, we have the integrated vent port, which basically just takes some silicone tubing and it runs it outside of the aircraft. So any electrolyte vapor, should there be a thermal runaway, it will go overboard the aircraft. What do these things give us as an operator? The built-in heaters, as I mentioned earlier, for the improved cold weather performance. You don't have to hang your aircraft in extremely cold temperatures and get them out and go run. Say you're in Alberta, Canada. You don't have that. We get faster engine starts, which that also results in cooler engine starts, which means you have less opportunity to have a hot start and then a really, really expensive engine overhaul or inspection because of that. That's another great thing about these batteries. You can also get successive engine starts within flight manual limitations. You can't just go out and do 10 engine starts if your flight manual says you're only allowed 3 per hour or something along that line. So don't go do that. Safety by testing, all the fun regulatory stuff. So there's a couple of TSOs and some DO-160 and DO-311 kind of type testing that your lithium-ion batteries should have. If you don't see these qualifications, I wouldn't recommend that you put that lithium-ion battery on your aircraft. This is how you can separate True Blue power battery from some of our competitors. So it should come with a TSO, C179A. That's your chargeable lithium-ion batteries and systems for aviation. That essentially is vetted by DO-311 currently. That's your minimum operational performance standards for the rechargeable lithium-ion battery systems. And then as sure most of us are familiar, any airborne equipment should be environmentally tested per DO-160. And then if it contains any kind of software, which our larger battery does, the software should be vetted per DO-178. So of course, how do we get these on our aircraft? Just like any other kind of system upgrade, your aircraft needs to be either type certed or STC'd with this product in the United States. And then if you're operating, in Brazil or Europe, their regulatory authorities such as EASA or something like that also apply. It's new and innovative technology. What that also means is the FAA and sometimes EASA and other regulatory authorities don't completely have all of the standards for what it takes to get this installed on your aircraft, so that might require some special considerations with your local ACO, such as an issue paper or special conditions that you have to meet outside of what the current regulations that they currently have on file are. But this is an evolving process. We actually talk with the FAA a lot on these committees for the lithium-ion technology regulations, and there's going to be more clear-cut regulations on getting these on the aircraft in the near future. So again, the big one here is that DO-311 testing. That's what gets you the TSO 179. This is the testing that gets you that seal of approval. And there's some key ones that you want to make sure any lithium-ion battery has, and that's given by these 5 points here. We actually take our batteries and we perform short circuits on them with the electronic protection enabled and disabled. And then we also charge it with those protections enabled and disabled in an overcharge condition. And then last but not least, we let everything just go by the wayside, and we make sure that case is going to contain a complete thermal runaway through the explosion containment test. And again, this is very important. Last bullet point. Not every manufacturer does this, especially in the experimental world. You can, so we stress to people to look for this, and buyer beware. Not all batteries are the exact same. Some of our operational characteristics. So you'll see some of the families of our batteries. And what we have here is a small battery. This is the TB17. It's 17 amp hours. And then these 4 battery cases are all the same size cases. They just they vary on the amp hour capacity depending on how many modules that we put in it. These modules contain 8 cells in series, and those will end up being a 35 amp hour battery, a 40 amp hour battery, 44, and a 46. But again, all the case sizes are the same. General electric characteristics. One of the key important things to note on a nickel-cadmium battery versus nickel-cadmium, lead-acid versus lithium-ion, we run a couple of volts higher. So that's pretty evident in our basic characteristics. We run nominally at about 26.4 volts. We charge with 28 just like you normally would nominally on your DC bus. But once we're done charging, we set usually about 2.5 volts higher than a lead acid. Most people, rule of thumb, when you get into an aircraft, you turn on power and you see 24 volts on your voltmeter with a lead acid battery, you know you're pretty well charged. Not the case if you see 24 volts with your lithium ion. If it's one of mine, it's probably time to go ahead and charge the battery. That means we're pretty low. The other cool thing about these batteries, very quick recharge times. Even at these are complete discharge batteries. We can get the large battery charged in 15 minutes because it can take all the way up to 400 amps. And that smaller battery, as I said, it will self-limit to 34 amps, and it still only takes 30 minutes to do that. The really good thing also is the weight difference. That 17 amp hour battery weighs under 16 pounds. The 44 amp hour battery weighs under 52. You can literally take the TB17 and hold it in the palm of your hand to walk around with it. Not only can you walk around with it, that battery has cold cranking amps of 850 amps that you can hold in your hand, 500 amps continuous. The bigger battery, the TB44, I can pick it up, takes 2 hands, and I can walk around with it. And again, I'm not a big guy. That battery, 1500 cranking amps, 750 continuous. The cells internal to those are made by a company called A123 Systems. And again, that's lithium iron phosphate technology. And what they do is they're about the size of a C-cell battery. You have 56 of them in the small battery and 152 in the other. You can see the configuration, 7 parallel times 8 series for that battery. That's how the 2 bricks are configured. And then you have the modules are 8 batteries in series times 19 of the modules in parallel for the TB44. The cases, lightweight materials, anodized aluminum for the TB17, powder-coated steel for the TB44. We'll go over some of the basic physical features. So the large battery, the TB44, every battery is going to come equipped as such. You have battery tie-down points. You have carrying handles on the side, the vent, a quick disconnect, a status indicator for the heater, and it also enables it so for cold mornings you can come out to the aircraft before the flight crew is going to get there, push that button, and it will and hold it down for 2 seconds. It has a little indicator LED. It will illuminate green. That lets you know that the heater circuitry, all internally powered by the battery, is activated. If the heater's actually working, that light will blink green and let you know. And that's on a timer, so it won't just sit there and do that day after day after day. So if the flight crew ends up not showing up, you haven't depleted your battery. And then we have 2 communications connectors. A small 4-pin, which contains resistive temperature device, and then an 18-pin connector. No, you do not have to use all 18 pins of that connector, so you don't have to run a giant harness to it. We gave options. There's A-Rink 429 data, there's discretes, and then there's also RS-232 data out of that. Very similar, but in a smaller package, we have the TB17. No quick disconnect on this. We use the standard terminals like you'll see on some of the Concorde and Gill batteries for some of the smaller aircraft. Same size, so you wouldn't have to change any of your terminals out on your wiring if you ever got one of these batteries. Another vent adapter. And then this connector here, 7 pins. There's no digital data in the form of ARINC or RS-232 data that comes out of this connector. This is all analog data, resistive temperature devices, and small relay discretes that you use for fault, fail, over temp, status indications, things of that nature. To that, if you do not want to go and design your own annunciator, or things of that nature, or wire these digital outputs to your avionics systems, we provide what are known as annunciator control units, or ACUs. These are roughly about 1 inch tall by about 3 inches wide, and they'll fit pretty easily in your instrument panel. They give you battery heat activation, so you, instead of having to go and push the button on the battery, you can actually do it remotely from the instrument panel. And it also gives you, as you can see, temperature, fault information, whether the battery heaters are on. So it's just a real nice, neat, small package with a 25-pin D-sub connector for communications connections to the back. Pretty simple install. Guidelines operating these batteries and maintaining them is really not all that different than what you're already used to for NiCad and NiCad and lead acid. We want you to maintain about 30 degrees C or 86 degrees Fahrenheit for storage. Don't store them in a shipping container on a runway in 122 degrees for 6 months. I've had people do that and then wonder why their batteries were discharged. So don't do that, just like you wouldn't do with a NiCad or lead acid. You don't have to maintain these at 100% state of charge, so you don't need trickle chargers for them. As a matter of fact, that's actually counterproductive. These batteries, you only have to charge them in storage once every 6 months because they maintain such a good shelf life. I have battery at my desk, a large one, that I charged it, and just for testing, I went and checked its state of charge. 3 months later, it was still at about 88% state of charge of just sitting there for 90 days. It's a very good battery. Capacity checks, those should be done at normal temperatures, roughly about 70 degrees. The reason why is if you have a cold battery, it's going to look like you have less capacity. If you have a hot battery, it's going to look like you have greater than the capacity you actually have. And that's true for no matter what chemistry you have. Things you should avoid: don't put it in a fire, so avoid external high temperature states. Physical damage, don't drop it, don't run it over with the tug, things like that. Don't overcharge it. Don't complete discharge it without recharging it in 7 days. And then don't short circuit the terminals. Funny story, I actually had a integration engineer take our small battery, the TB17, and he wanted to measure the terminals, so he put metal calipers across them. Don't do that. You'll get shocked. The battery was fine, the engineer was not. He got his hand zapped a little bit. Don't do that. Know your chemistry type and your operating requirements for safety. Just like any other battery shop, you might have big electrically isolated gloves, well ventilated areas, but still some things about our cells and things you will get information from us. If you ever get one of these batteries, it will come with a SDS sheet. You should know your first aid precautions and things like that in case somebody gets shocked. Don't wear your wedding ring when you're working on these. You don't want to arc weld that to your hand to a terminal. That's not good. Our lithium-ion battery products, you don't have to have special fire extinguishers or anything like that around in case something happens. Bucket of water. That's what we actually have in our facility in case somebody were to short the terminals or something like that. You literally have a step can, push the button, lid pops up, we drop the battery pack in the water. Very simple. Another good thing about this versus the cadmium and lead acid plated batteries, in the United States, and I stress in the United States, right now most municipalities allow for normal landfill disposal of lithium-ion batteries, just in the same way you could throw away a cell phone battery. But you need to check with the regulatory authority or the municipality in which you reside. So don't just, it changes sometimes per country and per city, but for the most part, these are legal for normal disposal. So the more important stuff, what you're going to do when you ever come across a lithium-ion battery and it looks new. If you buy one of our batteries, you will get its associated maintenance manual. These are not available on our website for download. It's proprietary in nature, so you have to own one of our batteries. However, if your aircraft gets an STC or it's type certified with this, you'll either have an AFM and a IFCA supplements for these batteries if it's an STC, or it will be integrated into your normal maintenance manual for your aircraft in things like Chapter 24 and Chapter 12 for servicing, and it will mimic most of the information that's in these batteries, battery manuals. Standard charges. We built these batteries to where you don't have to go and buy new charging equipment for your battery shops, new ground power units or anything like that. The TB17 charges at 28.8 volts constant potential. The larger battery, 300 millivolts less, 28.5, and it's constant potential. It's not constant current, it's constant potential. Most standard aircraft battery chargers that you have out there will have a setting that you can change that from constant potential to constant voltage, or excuse me, constant potential to constant current, and vice versa. You don't need any more than 60 amps charging current for this. This is by the book. Now, that being said, you can actually put the small battery and you can turn the charge current limiting up to 100 amps. That battery is still going to take itself back down to 34. The TB44, you can throw as much as 400 amps at it. It's all in what your charger can do, but by a rule of thumb, you don't need any more than 60. And you can use less. You can use 2 amps if you want to. It's just going to take you a lot longer to charge your battery. Constant current discharges for your capacity checks. So this has to be electronically controlled because as the battery voltage changes, the amperage will change to accordingly, automatically. 17 amps for the TB17 is needed, 46 amps for the TB44. And then for the TB44, since it has all of those advanced communications out of that large 18-pin connector, every 2 years is when you're going to do your maintenance cycles on either of these batteries, which is just a capacity check. But with the TB44, you need to have a laptop with this software installed, and it's a lot like what a lot of older avionics equipment have used in the past, things like Hyper-Terminal. It's just a quick little program that's free for download, and there's instructions in our manual, and what you're doing is you're actually going to go in after you do your capacity check after 2 years, and you're going to update the capacity of that battery so it knows what its new capacity is. You know, it'll leave the factory at 100, and say 2 years later it's at 98. You're going to tell it then at that 2 year point you're now at 98% capacity. So to do that, you're obviously going to need some connector cables and things like that, which we sell, or you can manufacture your own. There's diagrams in the manual. And then this is not necessary, but it's a good idea for troubleshooting. Since that battery does put out A-Rink 429, if your shop has an A-Rink 429 reader and you're troubleshooting an electric gremlin on your aircraft and you think it might be the battery, it's a good idea to analyze that bus and see if that battery is giving you any faults. It'll operate a lot in the same way that the RS-232 will, but with the RS-232, you have to physically type in and command all the time. It's not constantly updating, whereas the A-Rink 429, it's constantly going. It's a low-speed bus on this aircraft, and it's very easy to use. I went and did some troubleshooting. We hooked that up, and it was more so a way to vet that it wasn't my battery causing the problem. It was something else in the power distribution system. So it's a good tool to have. Charging procedures, you're going to do everything by the book, and again, this will either be in your IFCA, or it's going to be in the install manual, or it's going to be in Chapter 12 most likely. You're going to set your power supply on the 17 to 28.8. You're going to charge that battery until you see 700 milliamps or less of charging current. TB44 is very similar, it's just a smaller voltage, and then you limit the power supply to 60 amps, and you charge until you see 1 amp or less on the readout on your battery charger. That lets you know that we're top charged. Battery capacity check, again, very important. Do this at normal room temperatures. And then you're going to apply the charging procedure as per the manual for that particular model. And then you're going to apply the appropriate constant current. 17 amps for the small battery, 46 amps for the larger battery, the TB44. You're going to record the time, and you're going to divide that by 60. That gives you your time that you discharged in hours. And then you're going to multiply that time by the appropriate amp hours to get your capacity, either 17 or 46, depending on which battery you have. And then that last step here, you calculate milliamp hours for the TB44. So you're just going to multiply the last number by 1,000, and that's what you actually go back in on that software program and type into the battery to update its capacity. Given that, since these batteries are light, and a lot of people don't like to change batteries anyhow, if it's a nice day outside or you have good temperatures in the hangar and your battery equipment's mobile, you can completely do this on the aircraft if you have that capability. You don't have to take it into a battery shop to do these capacity checks. Obviously, you're going to want to disconnect it from the electrical system of the aircraft before you do all that, but it's completely doable on the aircraft. Some of our typical installations. Right now, this is the Bombardier Dash 8. We're type cert or STC'd on this. This is where the heater function really comes in great, and these batteries have been very great for this operator and the people that have installed this. There's 2 batteries in this aircraft, and they're actually in the left-hand forward nose. They have a primary and an auxiliary. Them being AvMax, they are in Canada, and they love the cold weather performance of these batteries to the exact scenario that I described earlier. They'll have flight crew call in, they'll come out, they'll open up these battery access doors, press the heater buttons. So it takes about 15 minutes, give or take, for these heaters to come up all the way down to negative 40 C. And then the batteries are optimal starting temperature, and they don't have to have a ground power unit to come out to start these big turboprop engines. It's all battery start on an aircraft that size, which is pretty phenomenal. Some closer up pictures, so you can see the vent adapter that they put in. So it's kind of a airflow scupper, if you will, and that battery bay door is here, and you can see in this picture you have the vent tubing that runs to the battery, to the top of the vent tube, quick disconnect connectors, and the cannon plugs for the communications. Behind this battery, or rather aft, is the second battery. In the center instrument panel overhead, they have the Annunciator control units, the ACUs. Since they have 2, they had us make another screen silt or fascia plate that says auxiliary battery, because all of ours will say main battery. But we can do things like that for custom installations. It's not a problem. This one's going to be releasing very soon to the market as a type-certed aircraft. This is the new Bell 505 Jet Ranger X. It's actually, I think it's going to be presented again this year at HEI. This was the list last year at HEI. This battery is held in the aft right-hand section, and it's the smaller battery, TB17. Again, this battery is better for rotary aircraft situations. It's much lighter, so it's a big seller with the helicopters. You can see the high-temp silicone tubing. Again, the 7-pin communications connector that will go, and this aircraft actually has all of its status information communicated to the Garmin glass cockpit screens inside, so it doesn't have a standalone annunciator or anything of that nature. It's all integrated to the Garmin CAS system. Relatively quick, but I usually have lots of questions that we'll cover on this. We have some of the summaries, and the reason why we do this is it's reduced weight. You'll have higher power, longer life. You get improved performance at the operating temperatures of either high or low. These also give you improved dispatch reliability. One of the benefits of this is that a lot of our operators that have installed these products now they can go to airfields that they used to not be able to go to because of the lack of ground support equipment. You don't need power carts with these batteries if they're at a good state of charge. So you can go to remote airfields that don't have a line service tech to hook up ground carts and things like that. So that also increases your dispatch reliability. The maintenance costs, as opposed to a NiCad battery, if you were to leave a NiCad battery on overnight and you come in your hangar, you've just cratered that battery, and you might get lucky and you might be able to recharge it. Chances are you might have to take that battery out, send it to a battery shop, and it just got really expensive. And if you didn't have another battery on the shelf, you may have just missed a trip. Hopefully it wasn't a revenue trip. Hopefully it wasn't for special missions like a medevac mission or something like that. Our battery, on the other hand, it will self-discharge till about 20 volts, any of our batteries, and then it will automatically turn itself off. That's at 0 point. If that happens, you come back into the hangar in the morning, you see the mistake, you turn the aircraft battery switch off, you charge the battery even just with a power cart, and then in about an hour, it'll be charged. There's no cratering, there's no new set 0 point. It's not going to skip a beat. You haven't done anything but lose maybe an hour. That's another very big benefit to this. The low carbon footprint. We don't have the toxicity of the NiCad, of the lead acid. Again, you can throw these away like you normally would just any other battery at your house. And even though it's lithium-ion, the maintenance, the installation, the operation of them, it's not really all that different than what you're currently using. Same battery chargers, same DC generation systems, whether it's alternator or DC generators on your aircraft. We usually just, at the maximum, is you'll turn up your point of regulation on your generation system a couple of volts higher, or maybe a 500 millivolts higher, just to get that top end charging point. Other than that, it's pretty simple. And then last but not least, you have myself on call 24/7 if you have one of these batteries, and I answer lots of phone calls, and I get people integrated into their aircraft. I help design a lot of our STCs and the integrations, and we're always there to support. And then we also have our baseline customer service. I will also be around for the day. I've got some pamphlets and some information and some business cards. If you have any specific questions about what programs we're on, what we're working on, what battery would be best for your aircraft, or we could talk anything else from USB chargers, DC to DC converters, inverters, any of your power needs, I'll be around. So at this point, I'll open it up to any questions. Yes, sir.
Are you looking to put those batteries on large cabin aircraft, such as Bombardier Dash?
Are we? So the question was, are we looking at putting these batteries on any wide-body aircraft, things like 737s, Q400s, things of that nature? And nope.
Something along the lines of a Gulfstream G550 or
Oh,
5000, 6000, 604.
I don't have any specifics on those particular airframes right now. We are in talks with pretty much any major OEM, and they may or may not have some batteries for evaluation, but I don't have any specifics on those particular programs right now. Any other questions? Yes?
What's the initial cost as opposed to like a Concorde?
It depends greatly on which battery and which size. Initial costs are more, but it's a longevity savings over time. And again, it's very subjective. I could get with you on the more specifics about your situation after the presentation to kind of discuss that, because it is very circumstantial. But as in the case of that aircraft, the Dash 8, lost it now. The Dash 8, those batteries ended up actually making money for the company within the first year because of the increased revenue, getting to go to other airports, the less maintenance, being an only 2-year maintenance cycle. The other important thing about these batteries is they have an 8-year lifespan. So you only have to check them every 2 years, and you're probably as long as you own your aircraft, because a lot of people own an aircraft 4 to 5 years and then they trade up, especially in the biz jet world. You know, a lot of people do own their aircraft longer, but it's not uncommon for only a few years. You may never have to change the battery.
What's the warranty on?
Warranty, standard warranty on all of our products is 2 years. Any other questions? Or, well, did I answer your questions? Yes, sir.
You talked about these lithium-ion batteries, and you hear about them running away either on an iPhone or another type of phone, and then Boeing had the same type of problem.
Correct.
On their new aircraft. What makes these now safer than what was?
Okay, exactly. So he's got a very good point. A lot of people hear lithium-ion, they hear about the things in the news with cell phones, laptop batteries, things like that catching fire. That's because they use those metal oxide chemistries where we use the iron phosphate. What that actually means is, although very reactive, those other chemistries are much more volatile and they run away quickly. Ours, when they run away, it's all one, contained by those metallic cases. Two, we have a battery management system internal to our batteries. And then we chose that chemistry because at the cell level, it's safer than the others. So even if it does have a runaway, it's not going to get as hot. It's not going to be as volatile. It's not going to explode. It simply just outgasses through the vent tube. We actually have testing that I witnessed the other day where you could actually go up and touch the battery when we forced it into one of those overrun situations, and it was fine. And the only time from my personal experience or anybody's experience with that I know of at the company that we've actually had a thermal event were when we forced the thermal event upon the battery to prove that it was safe during that DO311 testing. So to answer the question, we have smarter electronics in our battery management system, and then from the ground up with our chemistry, we chose a much more docile chemistry without sacrificing the battery performance characteristics. That's what cuts us apart from things like a Galaxy phone that catches fire.
You guys been talking to aircraft putting new batteries on?
Again, if you can name a manufacturer of an aircraft, we're probably in talks with them. Yes.
But they're not on there currently.
No. Any other questions? Yes, sir.
What exactly is being invented?
It's just an electrolyte vapor. So it's going to be the list of the chemical makeup of the vapor is actually quite long, and it's so we really just give it a generic term of electrolyte vapor. And and again, the only time we've ever seen this is when we had to force the battery to do this, and it kind of looks just kind of a foggy white kind of vapor is all it looks like.
How does it interact with aluminum?
It is a corrosive material, and that's why we use silicone tubing, and it vents outside the aircraft. So the natural airflow of the aircraft and just ambient outside pressure if the aircraft is sitting on the ramp, it'll just vent away from the aircraft to prevent corrosion internal to the aircraft. So if it is installed in your aircraft and you don't have the vent tube connected, well then you're going to have that on your structure, which is why we say put a vent tube in to get it outside the aircraft. Anyone else? Yes, sir.
Are you going to make 14 or 12 volt systems or all 28 volts?
It's something that we're looking at to see if we're going to have 12 volt system. We get a few inquiries every so often about it. It's being researched by some of our developed engineers and things like that and our business case managers. But currently right now I don't have anything on the books for a 12 volt aircraft battery. Yes, we're only on 28 volt systems at this point in time. Yes. Any other questions? All right. Well, if that's it, I appreciate it. Thank you.